In this video, we'll look at radical mechanisms. Specifically, we'll look at halogenation radical mechanisms of an alkane, but this is applicable to all radical mechanisms. There's always going to be the same three major characteristics. So, first of all, these three major characteristics that I'm talking about, it's a three-step process, radical mechanism. First step is an initiation step. This is where you go from a non-radical compound and you input some energy, either light, which could be denoted as h nu, where nu is just the frequency of the light that is being shined on in your system, or in addition, h is Planck's constant, just to give the energy that is actually being implemented into the system, or you can heat it, the reaction vessel. And what this will do is cause a homolytic cleavage of your non-radical compound. For instance, Br2 could homolytically cleave, and that will make two radical species. This is the initiation step because the whole mechanism requires radical species. So this initiates the entire mechanism by making the radical species. The next characteristic step is the propagation step. And the propagation step involves a radical and a non-radical compound. And what happens is you make a different radical and a different non-radical. So the propagation step is usually where the product is formed, because you go from the radical that is adding to the non-radical is going to end up making the product that you want, the different non-radical species. So next, the last characteristic is these termination steps. This is where you go from two radicals to make a non-radical compound. In essence, this is the reverse of the initiation step, and there is the most amount of termination steps possible of these three because there is many radicals that will be formed throughout the reaction process, and any two of them can come together to form the non-radical compound that terminates the radical mechanism. So there are many options here. Usually in an exam or a question of that sort, the termination steps can be ignored unless they're specifically asked for in the prompt for that particular question. The complete radical mechanism for bromination of ethane. So the reaction as written is so. So you have ethane. This reacts with Br2. We have some implementation of energy. In this case, I'm denoting as h nu. And this creates a bromoethane, where we have essentially replaced one of the hydrogens with a bromine. And there's a byproduct of HBr, which conserves the atoms and molecules involved. We've essentially replaced one hydrogen with one bromine, and here's the hydrogen bromine to conserve all atoms. So initially, we start with an initiation step. As I mentioned before, we go from a non-radical compound to two radicals. The energy that is input in the form of light in this case is what is required to cause this homolytic cleavage, where one electron goes to the bromine and one electron goes to the other bromine. That creates this bromine radical and another bromine radical. That completes the initiation step because now these bromine radicals will begin the propagation steps and make the entire mechanism continue like a chain, like a domino effect. So one such propagation step is where you take the bromine radical and react that with ethane initially. Now, this is something that's very important. So the carbon-hydrogen bonds are weaker than the carbon-carbon bonds, and we see that in the bond dissociation energy. So that is why the carbon-hydrogen bond cleaves first or cleaves as opposed to the carbon-carbon bond cleaving. There is also differences in carbon-hydrogen bonds. If there was a secondary or tertiary radical that could be formed, so if one of these carbons was more substituted than it is here, there would be a preference on which carbon-hydrogen bond will break. And again, as we saw in the last video, you can predict that based on the bond dissociation energies. In this case, there's no difference in the carbon-hydrogen bond strength for all of these because they're all just carbon-hydrogen bonds substituted by one methyl group. So they're all equivalent. So for ease of drawing, I chose this one here. And this homolytically cleaves where one of the electrons goes to the radical electron of the bromine, and that makes a hydrogen-bromine bond. So in essence, you can think of a bond forming between the hydrogen and the bromine, and that's what makes HBr here. And at the same time, you cleave one of the electrons in this sigma bond between the carbon and the hydrogen onto the carbon, which makes the carbon radical. Then this carbon radical can react with Br2 because Br2 has the weakest bond of what's available. A bromine-bromine bond is much weaker than a carbon-carbon or carbon-hydrogen bond. Again, you will see this in the bond dissociation energies, and these are usually included on an exam that includes radical mechanisms, so you can always reference it like that. If not, you should know the trends that I've talked about here. So the bromine-bromine bond is weaker than the other options, so the carbon radical comes in. One of those electrons forms a bond with the other electron from the bromine-bromine homolytic cleavage. So what that makes is the carbon-bromine bond, this bond here, and then you reform a bromine radical because this unpaired electron here is from this single-headed arrow from the homolytic cleavage of the bromine-bromine bond. Okay, so next we have the termination steps. Those are all the possible propagation steps because there is no other radical and non-radical combination. So the termination steps, recall, is two radicals coming together to make a non-radical species. So the most obvious one to me is the reverse of the initiation step, which is when you take two of the bromine radicals, react them together to form the bromine-bromine bond, which is Br2. This is the starting material that we started this entire process with. Next, you can take the carbon radical and react that with one of the bromine radicals, and this will make the product as well as the propagation step that we saw previously. So this is another possibility. Or you could take both of the carbon radicals and react them together, or two of them, I should say, two carbon radicals, and react them together and make butane, where you've now created this new carbon-carbon bond between two ethane equivalents. So you make butane. One last thing that you can do is react two carbon radicals again together, but now this is the most tricky because instead of just directly reacting the two radicals together to make the carbon-carbon bond like we see here, we are now going to take one of the carbon radical and react that with one of the carbon-hydrogen bonds and form a new carbon-hydrogen. So that is what's shown here. You create this new carbon-hydrogen bond, that's what's shown by these arrows. Then you can homolytically cleave onto this sigma bond and then use the radical here to create a pi bond. And there's a stabilization factor there because we know that these bonds are more stable, that these species are more stable than the counterpart. So because of that, this is possible, and we form a ethene in this case. So the takeaway from the termination steps is that there is many options, and there's going to be tons and tons of options, especially as the molecules get more complicated. In this case, this was just a simple ethane molecule, but you could have a more heavily substituted option in which you could have many of these alkene products and even the alkane products. So you have to pay very close attention to what the question is asking because it may want a specific propagation step. It may want a specific termination step. Usually the initiation step was going to be the same, so you just have to pay attention to what is clearly being asked. But the important thing to focus on is that you're going to create a radical in the initiation step, which requires energy, and then that radical causes a chain reaction to get all the way down to the product and these multiple termination steps. So one last thing to mention here is all of these side reactions with the multiple carbon radicals these are never going to be the major product. Because remember, the bromine-bromine bond is the weakest, so that means that you're going to have an abundance of the bromine radicals and only very small amounts of these carbon radicals. So if you have the small amounts of carbon radicals, it becomes less likely for two of them to come together and react in this way that I've shown. But it's not impossible. It's just usually considered negligible for the total reaction that is observed when you see it on just a large scale. So this is another reason why radical reactions aren't the most practical, because you get a bunch of byproducts, so it requires extensive purification to get the product the desired product. For the remainder of the video, we will look at a few key examples of types of questions that you would see on a homework assignment or exam. So here we're asked to draw two propagation steps that give different bromoalkanes for the following reaction. So the reaction is a simple bromination of this alkane. Br2 with light, with H nu is denoted here. And we are shown two products. The one that is with this tetrasubstituted carbon, and the other one where it's a secondary haloalkane as opposed to tertiary. And then we're also told that there are others. So we're specifically asked to draw the propagation step. So we need to recall a few things. One, the propagation step involves a radical and a non-radical, right? So radical as a reactant plus non-radical. So I'll just say NR now. So radical R plus non-radical makes a different non-radical. So D and R, so different non-radical, plus a different radical, Dr. Okay, so we know the initiation step is going to make bromine radicals, and the question is specifically asking for the propagation steps that makes the bromoalkanes. So let's just go through the possible propagation steps. So if we start with the bromine radical as our radical of in our scheme here for the propagation step, and our non-radical would then be the alkane, because if the non-radical was Br2, then we're simply just going to regenerate bromine, which is not a productive thing, not a productive mechanism. So here we have to consider which hydrogen is going to cleave. And most likely it's going to be this hydrogen, because if this heterolytically cleaves, this carbon-hydrogen bond, we're going to make a tertiary carbon radical, which we know is the most stable of the options that we have here. We have either tertiary position, secondary positions, and then 3 primary. So the tertiary position is going to create the radical. So what happens, this comes in with a single-headed arrow, this comes in single-headed arrow, we create a bromine hydrogen bond, and then we cleave this bond 1 electron onto that carbon here, this tertiary carbon. So what happens is you have HBr created, plus, which is our different non-radical, plus the different radical, the carbon radical. But the question was asking for the propagation step that makes the haloalkane. So this is not the answer. So the correct radical that we should use is the carbon radical, the one that we see here. We use this radical and then react that with Br2, we will get the bromoalkane, which is the product that the question is asking for. So if we use this carbon radical as the radical species and then Br2 as the non-radical species, we will now get a bromoalkane that is one of our products. So if we have this radical come in, it will attack here, this bromine will cleave, this bromine-bromine bond will cleave homolytically onto this carbon, and then the other electron will go onto the bromine like that. So what we end up with is this molecule here, which if we notice is one of the answers. So this is one of the propagation steps. This is one answer, the propagation steps that gives us the bromoalkane in question. And then the second part is the new radical, the different radical that's formed, which is just Br, the bromine radical. Br with an unpaired electron. So now, without having to go through the process now, we can think about this and save some time, right? So if we want the propagation steps that makes this bromoalkane, then we know that we need the radical to be at that carbon. And that is going to be the radical here in this scheme. So that is what we can start with here. Here's the radical that I'm referring to. React that with Br2. And then this will give us the other propagation step for the other bromoalkane, which again is what the question is asking for. So this gives us this species. And then again, we make the bromine radical. So here are the two propagation steps that give rise to the bromoalkanes that the question wants. So this is the type of stuff you'll see on an exam because it's pretty unreasonable to expect in the time constraints to draw the entirety of a radical mechanism because there's so many possible propagation steps and termination steps, etc. So this is much more common. Okay, here we have another question. This is a bit more challenging this time. We're asked about a specific termination step. So the question reads, draw the termination step that explains the formation of an alkane with 2 rings from this reaction. So again, we're asked about the specific termination step instead of a specific propagation step in this case. So we want 2 rings in our alkane product. So we can imagine, remember, if we had just a generic alkane and it's radical here like this, one of the termination steps that was originally introduced is that these 2 radicals could come together and form a new alkane. So this would form our CH2CH2R. So now this is the type of thing that's going to happen here, but we want to form the alkane that has 2 rings, and we're starting with this molecule. So in essence, we want this whole species to be a ring. So the termination step is simply going to be this radical plus the other cyclic radical, and then you create the bond from those 2 electrons. So I showed it like this. I've shown it like this just to avoid the clutter from this position here. But notice how this is completely the same, right? This is an achiral molecule because there's this plane of symmetry across this position here, and so it doesn't matter exactly where it's bound or how it's drawn. It's all equivalent. So you may wonder, well, how was this formed? Well, we know that we could form that in the propagation step where we have bromine radical reacting with just the cyclohexane. So any of these hydrogens can cleave like this, and that will give rise to the radical. And then that just happens twice, then those 2 can react together, and you make the alkane that has 2 rings. So the answer to this question is just this one here. All right, this is the last question for this video. You're asked to draw the complete mechanism that explains the formation of the following major products. And we are told that there's no need to include the termination steps. This is very common to be a part of a question to not include the termination steps if it's involved like this, and because the termination steps, there are so many and they usually don't contribute to product formation. There's such a small amount of the products that are formed that usually they can be ignored, the termination steps specifically. So this is a common thing. Now, we do need to include the initiation step and propagation steps, right? Those are not listed as not necessary. So our initiation step is simply going to be Br2 homolytically cleaving. And we need H nu to do this. We need our light or heat or some energy source. So here's our homolytic cleavage. We make 2 bromine radicals. Okay, and then this finishes the initiation step. We've now created our radicals that can then begin the propagation steps. So now we have a propagation step with a bromine radical and the alkane. In this case, it's cycloalkane. So we have Br minus, that's our radical, and we react that with our cycloalkane. Okay, now we need to consider which carbon-hydrogen bond is the weakest. And there's two that are about equally weak. There's this hydrogen, that would make a tertiary carbon radical there, and there's this hydrogen, which would also make a tertiary carbon radical. And again, we can use the products that were predicted here, or explained here, that we need to use this mechanism to explain their formation, that the radical has to form at this position or this position. So this is what's going to happen. So I will choose this carbon-hydrogen bond to break first for no particular reason. They could happen at the same time effectively. So you would form the carbon radical at this position. So our products from the reaction as drawn is HBr, like as usual, in the first initiation step. And then we create this carbon radical. And I'm redrawing it over here, again, to avoid clutter. This is an achiral molecule as well, again, because of the plane of symmetry across the ring. So there's no difference there between what I've drawn and what's here. I just simply rotated it or flipped it across the plane like this. So that makes the first propagation step. Then we can use this carbon radical and react it with Br2 to make the product. And since there's no need to draw the termination steps as indicated in our instructions, this is what's going to happen. This will be the major way that we form the product in the propagation step. So here's our radical. This will react with Br2. Causes homolytic cleavage as drawn. And then we will form now product A, or this is actually making product B. That makes this product here, because we've added the bromine to the alkyl chain off of the cyclic ring. Okay, now that is complete as far as way this question is reads. This is complete for this product here. Now we have to do the same two or similar two propagation steps for the other product. So again, propagation step. We take a radical and non-radical. So our bromine radical reacts with our cyclic alkane. But now we're going to break this bond, this carbon-hydrogen bond, because we broke the other one and already formed that product. So we need to explain this product here. So this will, carbon-hydrogen will homolytically cleave like shown, and then you form the carbon radical at the cyclic carbon. So that makes this product here, plus HBr as a byproduct. All right. And then there's one more propagation step to make the other product, where we use this carbon radical one more time. This reacts with the Br2. So we use this radical here to form carbon-bromine bond, and then this radical, and then we form the bromine radical. This bond homolytically cleaves. So we end with this product plus the bromine radical. And this bond I should have drawn as blue to show the mechanism, but we created this bond here in blue, and here's our bromine radical, again blue because of the mechanistic arrows. So this is the type of question that you should be prepared to do. They take some time, but they really explain what's going on in these radical reactions, and it's very useful to be able to do this, because then you can predict the products of a reaction that you may have never seen before. So just to conclude, the answer to this question is this initiation step, these two propagation steps, so this step, and the two propagation steps that make the other product. So this step 3 and step 4. Okay, hopefully that makes sense. That is all I have for this video, so I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have any questions, please feel free to leave them down in the comment section below, and I'll get to them as soon as I can. And with that, I hope you have a great day, and I'll see you all in the next video.